In this video, we're going to continue our study of Newton's laws of motion. Specifically here, we'll be looking at the force that a spring exerts, and we'll also talk about the details of how friction works. Let's start by looking at springs. Hooke's law tells us the formula for the force that a spring exerts. The force is equal to negative kx, where k is called the spring constant. The spring constant is just a measure of how strong or weak the spring is. So a stiffer spring will have a higher spring constant. Let's take a look at why there's a negative sign in Hooke's law. Here I've got three pictures of a spring. The top picture represents the spring in equilibrium. So in other words, when it's neither stretched or compressed. Think about what happens when you compress a spring. So if I compress a spring a distance x where x is less than 0, in other words, to the left of the equilibrium position, well then the spring wants to exert a force to the right. On the other hand, if I stretch my spring some distance greater than its equilibrium position, notice that what the spring wants to do is pull back or exert a force to the left. So that's why there's a minus sign in Hooke's law. If I stretch it in the positive direction, the force is in the negative direction, and vice versa. Let's take a look at what the units of the spring constant are. Whenever I ask you a question about units, I always want you to first just think about the formula. The spring constant is in the formula. The force of the spring is equal to negative kx. And so what I want to do is simply think about what units does k have to make this formula correct. We know that the units of force are newtons. We don't know what the units of k are, but we know the units of displacement or position are meters. And therefore, to make this formula work, what has to go in there is newtons per meter. And that is the unit of k. Now you could rewrite that in terms of kilograms and meters and seconds, but it makes sense to leave our unit for spring constant as newtons per meter, because you'll notice it tells us exactly what the spring constant means. The spring constant is simply telling you how many newtons it takes to stretch that spring 1 meter. So if I have a 15 newton per meter spring, what that's telling us is if I stretch that spring 1 meter, that would require a force of 15 newtons. The larger k is, the stronger the spring is. We're going to talk much more about springs later on in our videos, but for now that's really the main thing we need to understand about springs. Now let's get into the details of friction. So how does friction behave? If we just set up a very simple experiment, we would be able to learn a few things about friction. Some things we already know, though. We know that friction is always opposite the direction of motion. So if I'm pulling this block to the right, I know that friction is going to be acting to the left. For example, if I draw the free body diagram of my block, I'd have the normal force, I'd have the weight of the block, I would have the applied force that I'm exerting with that spring scale, and then I would have the force of friction. But what we want to look at now is we want to look at that force of friction in a little bit more detail. Imagine that I pull on the block with a little bit of force. Well, the block isn't necessarily going to move. And in fact, what we want to do is think about the following graph. Let's graph force of friction versus the applied force. So if I just pull a little bit on the block with my spring scale, the block isn't going to move yet. Well, we know from Newton's laws that if an object is at rest, the net force has to be 0. So notice Fa minus the force of friction has to be 0 if the block doesn't move. So if I pull a little bit on the block, the force of friction has to simply be equal to the force that I'm applying. Let's say I pull a little bit harder on the block. It still doesn't move. Again, those forces have to be the same. I pull a little bit harder on the block. It still doesn't move. So notice that the force of friction is not one value, but will increase as I apply a greater applied force. Think about the fact that if I'm not applying any force, if there's no applied force, then the force of friction also has to be 0. Now, at a certain point, I'm going to exert a force great enough that the object begins to move. And at that point, what we'll find is if we want to actually pull the block with a constant velocity, what we're going to find is that it takes a little bit less than the maximum force of friction. So once the block starts to move, to pull with a constant velocity will actually take a little bit less force than the maximum force of static friction. And so this area of the graph we call static friction. Static friction just means that the object is static, it's not moving. Once the object begins to move, we call this area of the graph kinetic friction. And what we find is that once we start moving the object, the friction is pretty much a constant value. Well, let's see how we can describe this mathematically. Oh, one other thing I should mention is that friction is proportional to the normal force. I'm sure you have a sense of this, that if you take two objects, the harder they're pushed together, the more friction there's going to be. You can try this with your hands. Hold your hands lightly together, rub them back and forth. You don't feel too much friction. Hold your hands tightly together, rub them back and forth. You feel a lot of friction. And that's, of course, why we do that when we want to warm up when it's cold. So the harder the surfaces are pushed together, the greater the friction, and of course that's related to the normal force. So when we look at static friction, what we find is that the friction can be anything between 0 and some maximum value. Here's how we write that with an equation. We say the force of static friction is less than or equal to mu s times Fn. Of course, Fn is just the normal force. Mu s is the coefficient of static friction. And we'll talk a little bit more about what these coefficients mean. Notice, therefore, that the force of static friction can be anything from 0 up to that maximum amount. Now, kinetic friction is pretty constant. So once the object is moving, the friction is basically the same. And so for kinetic friction, we have an equal sign in the formula. And again, we have this coefficient of kinetic friction. In general, the coefficient of static friction is greater than the coefficient of kinetic friction. And that's why in the graph we just talked about, we saw the friction increased until the object started to move, and then it went down a little bit and was constant after that. So the coefficient of static friction is generally greater. What are the units of mu? So take a look at one of these formulas and see if you can figure out what the units are. Well, you'll notice that we have units of newtons for friction. We're trying to figure out what the units of mu are. The units of the normal force are obviously also newtons. And so you'll notice that mu doesn't have any units. And the reason for that is you'll notice really what mu is, and I'll write it out for mu k. It's just the ratio of how much friction you get for a given normal force. And therefore, we're taking newtons and dividing by newtons. So no units for the coefficient of friction. So what is the coefficient of friction? Well, again, it's the ratio of the force of friction to the normal force. And it has to be determined for any two surfaces that you're interested in. So if I want to see what is the force of friction between a wood block and the table, well, that's going to be different than if I take a different object and put it on the table. And therefore, if we want to determine the coefficient of friction, we need to do it experimentally. We need to literally take one object, put it on another object, and figure out what applied force does it take to pull that object at a constant velocity. We know that if we're pulling that object at a constant velocity, then the applied force and the force of friction have to be the same, and therefore by measuring the applied force we can determine the force of friction and therefore figure out what mu is. One of the things that is maybe a little bit counterintuitive, you'll notice that area does not show up in our friction formulas. So the force of friction does not depend on the area of contact. Now, this is true within a reasonable value of different surface areas. But you can imagine if you have a really big surface area versus a very small one, then maybe this isn't quite true. And so one of the important things to understand about our laws of friction, that Fk is mu k times Fn, or Fs is mu s less than or equal to mu s Fn, is that these are empirical laws. So they don't have the same validity as something like Newton's second law. Basically what we're saying is when we experiment with friction, we find that pretty much friction obeys these laws. But friction is actually a very complicated phenomenon. Think about what's really going on. On the atomic level, it's really the fact that we've got this complex interaction between the atoms in the surface of the two materials. And so the underlying physics is incredibly complex. But what we find is pretty much on average, if we look at friction in the real world, these simple formulas do a pretty good job of representing how it works. But they're not perfect. So don't give these laws the same validity as you do the other things that we're talking about. Let's look at a conceptual question. Is it easier to push or pull a sled if there's friction? So think about that for a minute and then we'll take a look at it. Well, it turns out that it's easier to pull a sled than it is to push it. And in order to understand this, we want to draw out the free body diagram for the two situations. So let's start out by drawing the free body diagram for the person who's pushing the sled. And of course, we're actually drawing the free body diagram for the sled. Well, the sled has our usual forces acting on it. It's got the normal force. We've got the weight of the sled. Then we have the applied force that the person is exerting. Notice that that's down and to the right. That would be Fa. And then we have the force of kinetic friction as our person is pushing the sled. Since it's moving, it would be kinetic friction. For our person that's pulling the sled, if we draw the free body diagram for the sled, we see that the main difference in the free body diagram is the applied force is now not only to the right, but it's up. Again, we still have the normal force, we still have the weight of the sled, and we have the force of kinetic friction. So let's look at why it is that it's going to be harder to push the sled than it is to pull it. Let's look at the forces in the y direction. We know that the net force in the y direction is equal to the mass times the acceleration in the y direction. Now, our sled is not accelerating in the y direction. It's not going up into the air or going down into the ground. So the right-hand side has to be 0. Let's look at what are the forces acting. Well, the net force is just the sum of the forces. So in the y direction, we have the normal force up. We know we have mg down. But notice we also have a component of Fa. And since that component is down, I'm going to put in minus Fa sine theta. And that's got to equal 0. Or the normal force is equal to mg plus Fa sine theta. Notice that the normal force is bigger because you're pushing down. Now, if we look at our example of pulling, the net force in the y direction, again, is equal to may. Again, no acceleration. But now if we look at the forces, we can see that we have Fn acting up. We also have the component of Fa now acting in the positive direction, and only mg acting in the negative direction. Therefore, the normal force is going to be equal to mg minus Fa sine theta. Notice, therefore, that the normal force here is bigger, and the normal force here is smaller. Well, since the force of friction is equal to the coefficient of friction times the normal force, if the normal force is bigger, then the force of friction will be bigger, and therefore it will be harder to push the sled than it is to pull the sled. By the way, one quick note. Notice that here we put this minus sign in by hand. We're showing that Fa is down. So that means be really careful when you plug in an angle here, plug in the positive angle. Because we've already put in the fact that it's negative. Okay? So if you put in a negative angle there, then you would switch it back to positive again. Let's look at what's going on when we have something like a car tire that's rolling. So what type of friction is there between the tires of a car and the road? Is it static or kinetic? Think about that for a second, and then we'll talk about it. So a lot of times people think, well, the car is moving, so of course it's kinetic friction. But in fact, it's static friction. In fact, it's static friction unless you're doing a burnout. And by burnout, I mean you are spinning your tires relative to the pavement. But as long as your tires are not sliding on the pavement, then it's not kinetic friction. So by kinetic friction, we mean the two surfaces are sliding with respect to each other. If your car tire is rolling without slipping, there's no relative motion between the two surfaces. Okay, so as your tire is rolling along, these two surfaces are not sliding relative to each other, and therefore it's static friction. Let's talk about anti-lock brakes in a car. For those of you who are not familiar with what anti-lock brakes are, if your car is equipped with anti-lock brakes, it means that no matter how hard you push the brake pedal, your tires will not start sliding. You won't skid with anti-lock brakes. And the way that works is that each wheel is monitored for slipping, and if a wheel begins to lock up, your computer takes over and lessens the pressure going to those brake pads. So with a car that has anti-lock brakes, your tires never go into kinetic friction with the road. They never start sliding. It always stays static. So why would that be a good thing? Well, the reason is that you can stop faster. If your tires never slide, if you never skid, then you're always staying with static friction. And remember, in general, the coefficient of static friction is greater than the coefficient of kinetic friction. Therefore, the maximum static friction is greater than the kinetic friction. Remember our graph where we looked at that and we said the maximum kinetic friction, or sorry, the maximum static friction is greater than the kinetic friction. So again, that was static, this part of the graph, and that's kinetic. So if we want to stop as fast as we can, we always want to be right up here where the static friction is at a maximum. And that's what your anti-lock brake system does. It applies the brakes in such a way that they're just about to make the tires start skidding, but they don't ever let it get there. And so you can actually stop faster with anti-lock brakes. The other obviously big benefit is you can keep better control, because once your tires start sliding on the road, then you can't turn. You don't have any control of the car. Let's go through an example. Let's take a look at an example and see if we can apply what we've learned about friction. A force is exerted on a block as shown below. The coefficient of static friction is 0.58. Will the block move? What is the force of friction on the block? Okay. We want to always use our problem-solving strategies for Newton's laws that we've talked about in earlier videos. So I know the first step is to draw the free body diagram. In this particular case, we have a pretty straightforward free body diagram. The normal force is up. The weight of the object, mg, is down. We've got an applied force to the right. We've got a force of friction to the left. And sorry, that's going to be Fs for static friction. Anytime you have friction in a problem, the next thing you want to do is write down Newton's second law in the y direction. And the reason that we want to start in the y direction is we know that the force of friction, whether static or kinetic, is related to the normal force. Therefore, we've got to first figure out what the normal force is before we can calculate any forces of friction. So let's go ahead and look at Newton's second law in the y direction. If we look at the net force acting in the y direction, we can see there are only two forces acting. We've got the normal force acting up. We've got mg acting down, so Fn minus mg is equal to may. Now, our object is not accelerating in the y direction. It's not even moving up or down. And therefore, the right-hand side becomes 0, and we learn that the normal force is equal to mg. Notice that that's always going to be true when your object is on a flat surface and there are no other forces acting in the vertical direction. Now that we've got the normal force, we can calculate what the force of static friction is in this problem. The force of static friction is less than or equal to the coefficient of static friction times the normal force. Now, let's calculate that. So we've got a coefficient, which is 0.58. We've got the normal force, which is just mg. So mass of 10 kilograms times g of 9.8. And we get that the maximum force of static friction is 56.8 newtons. Now remember, with static friction, what we're calculating there is the maximum value it can have, but it can be anything from 0 up to that maximum value. So now we've got to look at the problem. The force that's being applied is 20 newtons. Notice that the maximum force of static friction is greater than the applied force. Well, obviously, it's not that the force of friction will then have that value, because that wouldn't make sense. We know that if the applied force is less than the maximum force of static friction, it means the object's not going to move. So block doesn't move. More importantly then, what is the value of the force of static friction in this problem? Well, the answer is it's got to be exactly 20 newtons. because we know that the block isn't going to move, and therefore the net force has to be 0 in the x direction. So the applied force and the force of static friction must be exactly the same. Let's look at one last problem. A man pulls a sled and a child with a combined mass of 20 kilograms. If he exerts a force of 50 newtons at an angle of 30 degrees and the coefficient of kinetic friction is 0.20, what is the acceleration of the sled? Once again, we always want to make sure that we're following those steps that I laid out in a previous video for solving Newton's law problems. So step 1, draw a free body diagram. So let's go ahead and do that. Again, we got the usual suspects. We've got the normal force acting up. We've got mg acting down. We've got an applied force, Fa, that is acting at an angle. So we'll call that angle theta. And then we also have a force of kinetic friction. So our object, in this case the sled, is going to be sliding, and therefore it's kinetic friction. Probably the best next step is to resolve any vectors that are not exclusively in the x or y direction. And we can see that that is just Fa. We've got the adjacent component, so that would be Fa cosine theta. And we have the vertical component, or opposite, so that would be Fa sine theta. Once we've got our forces resolved into x and y components, we now want to write down Newton's second law in each direction. Again, when it's a friction problem, you always want to start with the y direction because you know you need to know the normal force before you can calculate any frictional forces. Let's go ahead then and write F net y is equal to MAy. Again, when we see F net y, that means the net force in the y direction on the sled. Let's identify all of the forces acting. We definitely have the normal force acting up. We have the weight of the object mg acting down. But now we also have a component of Fa, so not the entire force, but just the vertical component, Fa sine theta. And that equals the mass times the acceleration in the y direction. Now in this example, again, the sled is not lifting off the ground or going down into the ground, so it's not in fact moving at all in the y direction, and so we can conclude that the acceleration is 0. Therefore, I can rearrange my formula and solve for the normal force. The normal force is mg minus Fa sine theta. And notice, as we looked at in a previous slide, the normal force is going to be less because that person is not only pulling to the side, but pulling up on the sled. And we know that that's going to minimize our friction. All right. You can now go ahead and calculate the normal force. I'll just tell you what I got. You should go ahead and check and make sure I did it right. I got a normal force of 171 newtons when I calculated it. Once we have the normal force, we can look at the x direction. The net force in the x direction is equal to the mass times the acceleration in the x direction. And of course, that's what we're trying to find, the acceleration of the sled. Next step, write down what the net force is. In this case, I can see I have the component of Fa in the x direction, so the horizontal component. And then I have the force of friction acting in the opposite direction. So Fa cosine theta minus Fk, that's got to equal Max. I can replace the force of friction with mu k Fn, since that's our definition for calculating the force of kinetic friction. So I have Fa cosine theta minus mu k Fn is equal to Max. And now solving algebraically, like we always want to do, Ax is equal to Fa cosine theta minus mu times the normal force, divided by the mass of the object. You should go ahead and plug in the values and make sure that you agree with me. My final answer was that the acceleration was 0.46 meters per second squared.